Okay, so welcome to the 10th and final video lecture in this course on quantum field theory. So in this lecture, we're going to show how we can use Feynman diagrams and Feynman rules in order to partially simplify this calculation of amplitudes that we've been wanting to do. So just as a reminder, in the previous lecture, we were going through this 5-step plan on how to calculate a scattering amplitude. So we've got down to we've covered the first 4 steps. So we've got down to step 5, which we didn't get onto in the last video. So in this video, we will. So step 5 is going to be to interpret our results. So interpret the terms that we get from using this Wick's theorem to grind down all the terms that we get. So we're going to interpret those terms with, or as maybe. Let's interpret them with or as Feynman diagrams. Okay, so this is where Feynman diagrams make their appearance. So they're particularly relevant for theories with interactions. Okay, so let's start with a simple, very, very simple example of a Feynman diagram. Okay, so let's start with a rule. And that rule is that these Feynman propagators that we've been dealing with, these are the propagators that appear from using Wick's theorem. So these propagators are going to be represented by straight lines. So in other words, we have, say, df of x minus y, so the Feynman diagram between the two space-time points. So as a reminder, this is the vacuum expectation value of the time-ordered product of my fields x and y. Well, this we're going to represent by a straight line like so. So between, oops, I have to draw the line. So between 2 points x and y as follows. Okay. So we have the space-time points labeled, and then we have a straight line running between them. Now, in this theory that we've been dealing with of the real scalar field, it's just a straight line, and we're not going to add anything else to it. So in some theories, well, actually many theories that have particles and antiparticles, you would also attach arrows to this. So for instance, when you look at QED, I'm sure you've been drawing Feynman diagrams in QED and QCD and so on, but there you have arrows on your lines, and those arrows are important. They tell you information about that particular state. For the real case, for this real scalar field, we don't have those arrows because, in a sense, not in a sense, it is true that the particle is the antiparticle in the real case. So we don't need to have an arrow. We just have a single line. Okay, that's a kind of the simplest example, not particularly interesting. Maybe a slightly more interesting example is one of the other cases we looked at. So we looked at the time-ordered product of 4 fields. Let me label them 1, 2, 3, and 4. Okay, so it's 4 space-time points. Okay, so this, in the previous video, we said this is going to be, well, let's just write it out. It would be 1 to 2, and 3 to 4. And it was 1 to 3, and then 2 to 4, and the remaining 1 to 4, and then 2 to 3. Okay, so we can, of course, also represent this as a diagram, or in fact, as 3 diagrams. Okay, so on the first one we have 1 going to 2, and we have 3 going to 4. Oops. We have that one, plus, then we had 1 going to 3, had 2 going to 4. So I'm going to indicate that they don't interact at this point. These are just freely propagating fields. So you can think of it as this little arrow hopping over it, so it doesn't interact with the other particle. Later on, we'll see what happens when we interact and when they meet at a point. And then the final one we have is 1 to 4 and 2 to 3. Okay, so we can represent this mathematical thing that we want to calculate in terms of these diagrams. Or conversely, we can go from these diagrams back up to some mathematics. So we know this will be the Feynman propagator. So this will be this term. Okay, so that's kind of the two very simple examples of using Feynman diagrams to represent just the propagator part. Okay, so we want to look at these Feynman diagrams in a slightly more trivial case than simply propagators in free space. So let's go back to the example theory that we've been looking at. So this phi to the 4 theory, when we've been looking at the process of 2-to-2 scattering. So we labeled it by Ka plus Kb going to the particle P1 plus P2. In the previous video, we worked out what the amplitude, the full amplitude for this process will look like. So we had these factors, these root 2e factors, and they sort of are coming along for the ride for the time being. And then we have these bits that we thought were a little bit more interesting. And we noticed that this was a series expansion in terms of lambda. So we have a term which is sort of lambda to the 0. We have a term which is linear with lambda. And then we have a lambda squared term and so on. So let's look at each term. Well, let's at least look at the first two. So let's look at the first one to begin with. So sort of the lambda to the 0th power. So I'm going to just focus on the bit between the two vacuum states, the vacuum expectation value to begin with. So I put a little tilde over that. The tilde does not include these root e factors that we could maybe come back to. Okay, so this is going to be 1. This is going to be the following term, and I'll remember to put in the t. So this is, of course, just equivalent to the state P1, P2, Ka, Kb. So this is just the overlap of these two asymptotic states. So what we know about this state is that, or this amplitude rather, is that it's going to be 0 if the initial state, so if the Ka, Kb state does not equal the P1, P2 state. Okay, so in other words, it's going to be 0 if scattering occurs. Okay, so it's 0 because if any scattering process occurs, what will happen is that the momenta and the energy of my initial state will change in some way. So, okay, let's imagine the specific case of elastic scattering of two particles. So elastic scattering, the energy might not change, but certainly the momentum will change in some direction. So we'll end up with Ka not equaling P1 and so on. Okay, so this first term is essentially boring. Okay, so it tells us it's 1 if no scattering occurs, and it's 0 if no scattering. Sorry, it's 0 if scattering does occur. So this is boring. We don't care so much about it. So the first interesting term comes in with the lambda 1 term. Okay, so let's have a look at it. It's going to be much thin. So again, we're doing 2-to-2 scattering. Let me rewrite it again so it's on the page. Lambda, we had the d4x, we had the 0, and then we needed to do the time ordering of the following terms. Okay. So we know what to do with this expression, right? We're supposed to use Wick's theorem to sort of simplify everything and well, basically, hopefully turn everything into something that we can just write as a function, so like a Feynman propagator. Okay, so that's apply Wick's theorems. This was our step 4. Okay, so when we apply Wick's theorem, we'll get terms. Okay, well, we'll get lots and lots of terms from this expression, but they're going to look like terms like 0. Okay, we're going to have the normal ordering with all of these states in here. This is obviously not interesting. Normal ordering, remember, brings all of my annihilation operators to the right. So they're going to hit that vacuum state and give me 0. So those terms aren't going to be interesting. The interesting terms we're going to get are going to be terms with Feynman propagators. Okay? Going to be many, many Feynman propagator terms. Okay, so let's look at the types of terms we can get. say we're going to have two types of interesting, i.e. non-zero contraction terms. Okay, so the first example we can get, so we can get contractions with the phi fields. Okay, so we have 4 phi fields in here, so we can do contractions with phi and a phi, so like this, so phi 1, phi 2. So we know what this is. This is just the Feynman propagator. Okay, so we've met this a few times now. So we know how to deal with those terms. But there's a new thing that you can see that we're going to get here, which is we can get a contraction. So that's our first term. The second one, we can get a contraction with phi with one of our terms, which is just a. So let's say k a. We should also do contractions of these types of terms. Okay, so we need to figure out what this actually gives, okay? Because we know this gives the Feynman propagator. We need to figure out what's going on with this type of term. So, put it in brackets. So we're working out what this contraction is. So what this means is we do 0. We put these states between two vacuum states with the time ordering symbol following way. So we have to work out what this is. So, in the previous case, this just gives us a Feynman propagator. Let's see what it gives us for this case with a single A. So to proceed, we can write out our expression for phi. We know how to express phi. We've done it many, many times now, so it's going to be 0, and it's going to be A, B, E, I, X. And I'm using P here, but I should mention P is a dummy index in this case. It's not linked to the P1 or P2 that we have in the final states, so I could have labeled this Q or AA. Okay, so we're interested in evaluating this. So you could ask, well, what's happened to the normal ordering process? Well, it's still there, but we're imagining the case where this produces an initial particle. So that's definitely at the start of the interaction. Okay, so this is the time ordered product that we want to consider. Okay, where this is the initial state. So we've dealt with this a lot of times now. We know what we have to do. We look at this combination, an A with an A dagger term. We use the commutation relation. We're going to get a 2 pi cubed a delta function that we can deal with. So let's just skip the details a little bit and write down what the answer will be. I say we've covered it in some of the earlier lectures. So we're going to get 2 pi cubed delta 3 p minus q from the commutation relation between A and A dagger. We need the e to the minus I e dot x still. And yeah, so we would, I guess, have the 0, 0 left over, which is simply going to be 1. Okay, so this we can integrate. We can integrate the delta function. It just sets p equal to k. Yeah, why did I write q? This should be a k. Okay. It's the momentum from this state. Okay, so we integrate this. We're going to set p equal to q. Again, we've seen this before, so this will now become 2 omega AA. We'll have an e to the minus I ka dot x term. The 0, 0 becomes 1. So we've worked out, in other words, what this contraction is of phi with, in this case, a creation operator, which is setting up my initial state. So I've used omega here. Omega's, I've been interchangeably using omega and energy because we know omega is energy. We're using natural units, so omega and energy are the same quantities. Let's actually use the energy symbol. Because if we do that, we can actually see how to deal with this 1 over root 2e factor. So to see that, we can see that the full calculation for the amplitude actually has a root 2e factor for each of my initial state particles. So in here is a term that we are going to find cancels precisely with this root 2 factor we find here. Okay, and the reason why is because here we're dealing with sort of this normalized amplitude pieces that didn't have the root 2 factors at the front. Okay, so in other words, this A tilde was all of this piece without the root 2 factors. The full amplitude then is going to be the A tilde piece that we've just been looking at times this root 2 EA term. We're going to find it cancels. In other words, I could say that rather than doing it with another way we could write this is we could write that root 2 EKA phi with a dagger. So this thing, so this is going to be 0 E phi with the state Ka. Okay, so sometimes, and I'll follow this notation, you see this written as simply phi with the state Ka. Okay, so you're contracting phi with one of the particles in my initial state. This is what this notation means. When I do the contraction inside the state, it's simply telling me I'm doing this contraction with, and because of the normalization of my states, I get this extra root 2 EA factor. So that you know what this is. This is going to be e to the minus I Ka dot x. So this is a second, if you like, class of contracting these fields. Okay, so when we just have fields, when we contract them, we get the Feynman propagator. When we contract a field with a creation operator, which is creating my initial state particles, so I can write it like this, and the result is rather than getting the Feynman propagator, we simply get an e to the minus ikx factor. Okay, so there's going to be a Feynman rule associated with this. So we call these pieces, these types of contractions, external leg pieces, because we're contracting particles at asymptotic infinity, right? Our initial states at technically t equals time minus infinity. We're contracting that with one of our field operators. This external leg. There's two ways we're going to write it. So if it's contracted with an initial state, so we call this an incoming state, you get an e to the minus ikx factor. And if we do the conjugate version, this version, we'll get an e to the I p dot x. And this is an example of an outgoing external leg state. Okay, so that's mathematically what's going on. And the way we can represent it as a diagram is with straight lines. Okay, so for instance, if we consider the state coming into the point x with some momenta k, this is an incoming state. So here I'm using the convention used in the scattering processes where time flows from left to right across the page. So this, as we said, gets a e to the minus ikx factor. And then we can also have outgoing states, be lines that move towards the right-hand side of the page. This has a momentum p, it's an e to the I p dot x. Okay. So those are the types of things we're going to get by using Wick's theorems. So we're going to get Feynman propagator terms, and we're going to get terms like these ones, which are associated with external leg factors. Okay, so now that we've kind of classified the two types of objects we can get from Wick's theorem, let's actually look at the amplitude, this 2 to 2 scattering amplitude in phi to the 4 theory, and we're going to look at the term which is linear in lambda. Okay, let me rewrite it again. And this time I'm going to write it as the time-ordered product of P1, P2, phi x, phi x, phi x. Okay, so now we want to apply Wick's theorem. Let's look at all of the ways that we can, in principle, apply Wick's theorem. Okay, so there's going to be many possibilities here, so let's consider them. We want to do contractions. Let's write P1, P2. So I write phi to the 4 as 4 separate phi fields precisely for this contraction process. So help me to make sure I contract fields properly. Okay, so one way I could contract this is as follows. So we could do P1 with the first phi x, 2 with the second one, and yeah, that's one way we could do it. Or we could do look at the example where let's contract with the first one again, let's contract with the second one again, and we just swap the order of the contractions with the k fields. So remember, Wick's theorem tells us we have to do all of the possible contractions. Okay, so we have to go through and figure out all possibilities. Okay, Wick's theorem tells us. So in particular, I want to think about every other way of contracting. So we're doing a phi x here with a p or a k. Okay, so here it's always a phi x connects to one of the p's or one of the k's. Okay, so it turns out that there's 4 factorial ways you can do this, so 24 ways. I'll leave it up to you to count them, but if you just draw these lines, you can see that that's what you'll end up with. Okay, so there's 24 separate ways that you can connect up these p's and the x's. So this is a special type of diagram, so I'm going to define it here as a connected type of diagram. Okay, so when we actually draw the Feynman diagram associated with this, it'll make sense, but let me just introduce the term, because that's one way you can do all of these contractions, and there's another way which leads to disconnected diagrams. So we can also do the following. So let's write out our term again. Okay, we can do, or we can look at the case where we contract, let's say we contract, do it in a different color. Let's say we contract P1 with Ka, P2 with Kb, and then we contract the fields just with themselves. So in other words, here our phi fields aren't ever contracted with our p's or with our k field. Okay, so again, in principle, we should write down every other way that we can do this type of contraction. Need to do all of the p's with k's and all of the phi's with itself. Okay, so this whole bunch of diagrams that we get, these are going to be examples of disconnected diagrams. Going to turn out that the most interesting ones are the connected diagrams. Let's finish by just closing the bracket. Okay, so we've this full expression then is reasonably complicated. We have this prefactor at the front, and then we have every possible way of doing these contractions such that we contract up every possible field. Okay. So as I said, the connected diagrams are the more interesting ones. So let's think about what they look like in a little bit more detail. Connected terms take the form of the following. Okay, so we've determined what the mathematical factor associated with this connection process should be when we have a phi field with internal or an external fields, right? We just get an exponential factor. What we're going to have, minus I lambda over 4 factorial d4x. This was the term that just came along. And then from every contraction piece, we're going to pick up an exponential. We'll get an e to the ip1.x and e to the ip2.x minus ka.x. That's what we would get from this first way of doing the contractions. And then from the second process, well, we'll get precisely the same factor here, okay? Because we're still doing a, one x field with a k field. We've swapped which one it is, but since these phi x fields are all the same, it doesn't matter. Okay? So once we add together all of the possible terms, so remember there's 4 factorial, there's 24 ways of doing this, we should multiply, add together all 24 possibilities. Okay, so we're going to multiply by 24. Now, this now makes sense of why phi to the 4 theory, or it might make some sense, why it comes with this 4 factorial term in the definition of the coupling constant. So the reason it comes to this 4 factorial term is simply so that we can cancel with this factor of 24, because 4 factorial is 24. Okay, so all of those 24 diagrams that we have here, you know what they give? They give minus I lambda d4x. Have all of these. So in fact, we can, for this particular example, we can actually work out what this is if we, or rather, we can write it in a different way. We can write this in terms of a 4-dimensional delta function, using the definition of the delta function in terms of the exponential. And this factor of 2 pi to the 4 just comes because of our definitions. Okay, so that's what the amplitude actually gives. So we've used we've just used the mathematics that we've worked out by applying Wick's theorem and so on. However, we can also represent all of this with a diagram. Let's show you what the diagram should look like. So what we're doing is, we have we have initial points, or initial states, A and B, coming into some space-time point X, where it meets some fields, and we have some other particles in the final state. So I'm going to represent it in the following way. I have states Ka, AB coming into what we call a vertex, and they're going out again to our asymptotic states P1 and P2. Okay, so our vertex is this point X in the mathematics we've been using above. So this is an example of a vertex. So in this diagram we have vertices, and then we also have all of these 4 lines. These are all external legs. They're all connected to our asymptotic states, our particles at infinity. So, one way of calculating this amplitude is to go through this whole calculation as we've done it. Okay, it's completely doable, but just a little bit messy. Or we can kind of abstract some rules out of this process and try and sort of shortcut the whole process. So this is what the method of Feynman diagrams and the Feynman rules associated with diagrams allow you to do. Okay, so they allow you to very quickly, basically automatically, write down what the answer should be for that amplitude, rather than going through this slightly tedious process, this 5-step tedious process. Let me tell you the rules in this case. So how do we build these amplitudes? And mostly, well, at this point, I'm going to tell you what they are in position space, because it's mostly what we've been working in. At the end, I'll maybe mention momentum space as well. Okay, so some of the rules we've already said, or we've already spoken about. So when we have these external leg factors, we need to have, well, we draw a straight line. Okay, so they're represented by a straight line as they are here. They come into some space-time point, and we have a factor associated with them, this exponential factor. Okay, so we have a e to the minus, and it's either a minus sign for the incoming or a plus sign for the outgoing states. Okay. For the vertex, so in this particular example, we see that our amplitude is proportional to this factor of minus I lambda. Okay, so it's minus I lambda as a d4x piece, and it has all of these external leg pieces. Okay, so we're saying we know how to deal with the external legs. We have a rule for those. I'm going to give you a rule for the vertex. So the rule that we can use is that at each vertex, we have this factor of minus I lambda. So the vertex factor is specific to the theory that you're thinking about. So in this specific theory, this definition of our coupling constants and so on, the factor we get is the factor of minus I lambda. This vertex is associated with this point x. And we see in our amplitude, though, this vertex factor doesn't come alone. It comes with the d4x piece. Okay, so what we have to do is to include this integral. Okay, so in our rules, we have to integrate, I'll say the positions, but I guess they're really space-time points, or rather coordinates of the vertices over all space-time. So that's what the d4x term is doing in our expression. Okay, so in this simple example, what we could do is just draw this diagram. Say, well, I now want to calculate the amplitude. So, okay, I've got a vertex factor. Sorry, I've got an external leg factor for each particle. So that gives me these 4 exponential terms. I've got a vertex, just a single vertex in this diagram. So I get this factor of minus I lambda. And then I need to remember to integrate over all possible space-time positions of where this vertex would be. So I include this d4x term. Okay, so if I draw this diagram and just apply these rules, I would end up at this result, okay, without having gone through all of those other processes, those other 5 steps we've gone through. This is a particularly simple example. So there are other rules that will show up in other diagrams. So in this particular diagram, we have no propagator states. So that's to say, the only particles only propagating from asymptotic affinity into the point x. We don't have any fields, where it propagates from some point 1 to another point 2. But if we did have a diagram that it would have a propagator in it, we would need to include a factor for the propagator. And there's a subtlety. We have to be careful counting the number of diagrams that contribute to a given process. So for that, there's this so-called symmetry factor that you can work out for a given diagram. Okay, so the symmetry factor is basically defined to be the number of combinations relative to this specific example. Okay, so here we set it up here. Here we had 4 factorial ways of essentially drawing the same process, what showed up here. If we consider other types of scattering processes that might have multiple vertices, the vertex factor can be different. So we have to correct for that for a given process. The symmetry factors are typically factors of 2 or 4 or 8 or something. They're a bit more of a cumbersome thing in this phi to the 4 theory than in other theories you'll think about. So if you think about QED, QCD, these symmetry factors don't tend to be such a problem. Phi to the 4 theory, because all of these phi fields are the same, these combinatoric factors are a little bit more annoying. But, you know, again, in principle, there's a well-defined way to always work out what this symmetry factor is. So put these bottom two in a box because they're not in this particular example that we've looked at. But that's not to say that they're not important. They are important parts of the Feynman rules. Okay, so for this 2-2 scattering process, we've discussed now in detail these connected diagrams, which we said are the most interested when it comes to calculating cross sections. Let me just very briefly consider these disconnected diagrams that also appeared. Okay, so let's consider one example. Let's draw what it would look like as a diagram. So let's do P1, P2. Then we have our 4 phi fields, KA, KB. Okay, so what will this look like? Well, in our disconnected diagrams, we connect P's with the K's and the phi's with the phi's. So as a diagram, we would draw this in the following way. So we would have KA going across to P1, have KB, P2, and then sort of somewhere else in the diagram, we're going to have X, and this propagator, well, it goes from X to X, so let's draw it in the following way. So it propagates back to itself, coordinate X, and then we have it happening with 2 separate fields. You know, this could be the top one, the right one could be the bottom one. Okay, so so we can represent this type of amplitude with a diagram like so. So this is a special type of diagram. So this is an example of what's known as a vacuum diagram. Okay, so in particular, this sort of bubble piece. These, as we said, don't contribute to cross sections. I guess from the way the diagram is drawn, you can sort of maybe see why. In the actual asymptotic states, well, they just propagate across without interacting in any way. So I'm not going to go into any more than that. So the proof for why these don't contribute to cross sections beyond this course, simply because of time constraints. But as I said, from the way the diagram is drawn, you can already get a feeling that, well, particles, these asymptotic states, aren't actually interacting with each other. So it's clearly something odd is going on here. So for cross sections, if you're only interested in cross sections, we only need to consider the class of diagrams, which are connected diagrams. Just to be super clear again, so this is a disconnected diagram because we have this little bubble figure of 8 shape, which is disconnected from the rest of the diagram. That looks different from this diagram where every external leg is connected up to some type. Okay? When you have diagrams that fall into this class, you're interested in cross sections. We don't need to draw them. We don't need to work out what the amplitude is because they're not going to contribute to cross-section calculation. Okay, so I next want to discuss a very quick example of the advantage of Feynman rules, which in the end are that they allow you to very quickly write down what the amplitude for a process is. So let's consider not a case of 2-particle to 2-particle scattering, but single particle to single particle scattering. So let's imagine we have a state K going to some state P. Okay, so with this Feynman technology that we've been developing, what we should do is start by drawing a diagram for the process. So we have some external leg K, and we're going to have some external leg P, and we have to connect them up in some way. So what we do is we connect these external legs up to a vertex at some point. Okay, we actually want an interaction to happen. I mean, in principle, we could consider the process x goes to p, but that's boring. That's a no scattering process. So we want something to happen as this thing goes from minus infinity to infinity. Okay. So we need to connect it up to a vertex of some type. Now, in this phi to the 4 theory, we saw an example of a vertex. Okay, we saw it was 4 particles. That's good. Here's the type of vertex that we're going to get all of the time in phi to the 4 theory. Okay, so we need to have 4 legs coming in to meet at a point. So here, to make use of this vertex, we have, well, the 2 legs come in from the external states, and we're going to have 2 other legs. So we need to do something with these, and they can't, they can't just go off to infinity in some way, because then we would have a 2 to 2 scattering process. So we must, the only thing we can do is connect them up in some way so that they don't end up at asymptotic infinity. This is, for instance, what you could do. You connect them up in the following way. Okay, so then we apply our Feynman rules, and we're going to use the position space Feynman rules. Okay, so to write down this amplitude, this one-to-one scattering amplitude, okay, we were told that we have to put in a e to the minus I k dot x factor and an e to the I p dot x factor for the incoming and the outgoing states. We need a factor of minus I lambda for the vertex, and we should integrate over all possible positions of that vertex. So we get a d4x term. Here, we do actually end up with a propagator factor. Okay, so here we have a particle a little bit odd. It propagates from the point x back to the point x. But it is a propagator, so we should put it in. It's going to be like this. And then this diagram also has a symmetry factor. So I'm just going to tell you what it is. It turns out that we need to divide by the symmetry factor, which is a factor of 2. Don't really have time in this course to go into details of how you calculate the symmetry factor, and it's not particularly interesting either. It's just a combinatorics thing. Let me just write it down. It's a factor of 2. Peskin and Schroeder has a nice explanation of symmetry factors if you want more details. So in principle, that's it, right? We have written down the full answer. Okay, there it is. So you can see the advantage. We didn't have to go through all these 5 steps of expanding the S matrix and so on and so on. You can very quickly get to the answer. So let me show you another way that we can write this. So as I said, here we use what are called the position space Feynman rules, but we know how to write this propagator. So let me remind you of the definition of a propagator that we worked out. So we said this was an integral over d4p, 2 pi to the 4. We had an I to the e minus I e x minus y, and then we had this p squared minus m squared, and we used the I epsilon prescription. So really I haven't written it here, but really we should technically be writing in the limit that epsilon goes to 0, but most books tend not to write it. So I think we derived this, I think it was in lecture 7, possibly lecture 6, but I think in 7. So let's substitute that into our expression. And let's see what we get. So the expression above has this at, well, it's an x minus x term. Okay, so we just get a factor of I e to the, with the x minus x term here, we'll get just a factor of e to the 0, which is 1. So the propagator can be written in this way. Okay, so what you may see here is that the only x dependence is in these exponentials. So we can actually gather these together and integrate over x, and we'll get a delta function. I don't know what the answer would be. Get this vertex factor, bring the integral to the front. Let's bring this propagator factor to the front. And then from this, we can rewrite this as a delta function. It's a 2 pi to the 4 times delta 4 And we have, that's what it is, k minus p. Okay, so notice that here we have written the amplitude purely in terms of momentum terms. Okay, there is no more, we're no more integrating over x, we're simply integrating over d4p. So this tells us that we could, or gives a hint of the fact that we could also write down Feynman rules not just in position space as we have done, but also in momentum space. Okay, so let me tell you what the momentum space rules are. Okay, so some of them are exactly as we had before. Okay, so we have well, we have a for each vertex. We have the factor of minus I lambda. Okay, so this is going through the diagram. So we've got the vertex at the front, the minus I lambda factor. We need still to include the symmetry factor. So when I say include it, I guess I should say divide by it. So we do that as before, and it's the same symmetry factor. The symmetry factor does not depend on whether you're in position space or in momentum space. We need to have factors for the external line or external leg. And you'll note that above, in this momentum space, the external leg factors are particularly simple. Okay, you might wonder where they are. You could wonder that because they simply take the value of 1. Okay, so for each external leg, just have a factor of 1. So that's very easy to deal with. We get a factor for the propagator. Okay, so in this instance, the propagator was this loop. Okay, and the term associated with the propagator is this factor I over p squared minus m squared plus I epsilon. So we get an I p squared plus I epsilon. We have to integrate over something. So in position space, we integrate it over d4x. In momentum space, you see that we integrate over d4p. We need to integrate over the momenta, and let's think about what the momenta is. Let's go back and double check, because I perhaps wasn't as careful as I could have been with my notation above. And indeed, I wasn't as careful as I could have been. So this p we have here is a dummy index. So actually, let me rewrite it. Q everywhere. The reason for doing that is because we're considering the scattering process of k going to p. So I don't mean to give you the impression that the propagator depends on p in some way. It doesn't. Depending on a variable q. Okay, so you could ask, well, what the heck is this q factor then? So q is going to be the momenta in the loop. Okay, so the momentum that's flowing around this loop. So if you don't have a loop, if you have a diagram without a loop, you don't have to, well, you don't get a propagator and you're not going to integrate over it. But if you do have a loop, we need to integrate this over this loop momentum. So we have to include a factor for that. So in this case, it's actually, since we're talking about general rules, let's go back to d4p because I've used p in the propagator factor above. And that's it. So again, it's a fairly short list, 5 points. So it's all the same. It involves the same thing. So the vertex factor, the external legs, the propagators, the symmetry factor, and integrating somewhere. But in momentum space, it changes slightly. The external leg factors are a little bit easier to deal with. In practice, at least in my life as a physicist, almost all of the time I've written down the amplitude using these momentum space Feynman rules. It's occasionally I've gone back to position space rules for particular problems, but most times it's more convenient to work with these momentum space Feynman rules. But they work in essentially the same way, right? So you start by drawing a diagram for the process that you want, and then you attach, you look at each part of your diagram and use these factors. So for instance, the external legs, you put in those factors. For propagators, you put in the other factors. For the vertex, you put in the other factors. So Feynman rules really make it very easy to in the end find and obtain the answer for the amplitude. You end up with nice compact expressions such as this one. So in fact, there's one thing I forgot to mention in these rules, and you can see it in the expression above. We have this delta function that also needs to go into our momentum space Feynman rules. Let's think about what this momentum function is doing. So basically, it's just encoding energy and momentum conservation across the diagram. So what we have is it imposes it, and in particular at the vertex. So we have K flowing into the vertex, so we need to have P flowing out. That's what this 2 pi 4 delta 4 factor does. Okay, so let's write this as force and force the conservation of energy momentum each vertex. So above we only have one vertex. Typically we do this, as I said, with the delta 4, and we have the sum over all of the momenta at the vertex. Okay. That's the final bit that we need to include in our momentum space Feynman rule. Okay, so that more or less brings us to the end of the course. I'm going to summarize by drawing a diagram that I've stolen from this book, Quantum Field Theory for the Gifted Amateur by Tom Lancaster and Stephen Blundell. It's quite a nice little book. You have to be a very gifted amateur, I think, to understand it. It's not a trivial book to understand. But they have this nice diagram that summarizes basically everything that we have done. So let me reproduce it for you. So what we started with is we started with a theory which we defined with the Lagrangian. Okay, and we sort of broke it into two pieces. So our Lagrangian had a piece that was a free part, and it had a piece where we had the interacting terms. So in the first, 5 or so lectures, we thought about this free part in a lot of detail. And in particular, we thought about this process of canonical quantization. Okay, so there's a pretty straightforward, at least for the real scalar field, prescription, some steps that you can step through to go from your classical field to the quantum field with this canonical quantization procedure. Okay, so that was great. We learned a lot about quantum field theory and how particles emerge and so on. But free fields are free theories are kind of limited in that no interactions occur, particle number doesn't change, it doesn't look much like our universe. So we needed to think about the interacting piece. So the important part for the interacting piece is that we needed to find an expression for the S matrix. And once we had that, to make progress, there was this expansion, so-called Dyson's expansion for S, that we make use of. This was what we were using to calculate or to make the process calculable. Otherwise, it was very, very tricky. Once we got this Dyson's expansion, we then applied procedure, which was the Wick theorem. So we sort of simplified all of the terms we got using Wick's theorem and turned them into propagators and external leg pieces. And then we started to work out some processes, and from that we were able to hopefully, I was trying to show you how you can start to pull out the fact that there are certain rules associated with the diagrams that you get. So there's kind of a structured way that that you can organize the calculations. So we looked at a couple of examples to see how you can start to infer the Feynman rules about what the external leg factor should be, what the vertex factor should be, what the propagator factor should be, and so on. And then once you have the Feynman rules, in principle, you can actually forget about all of the stuff above if the thing that you're interested in is calculating amplitudes. I guess it should say in brackets here, cross sections. We didn't get quite to the point of actually calculating or going from amplitudes to cross sections. I just told you that cross sections are proportional to the absolute magnitude squared of the amplitudes. So it's a little bit more detail there to actually get the full cross sectional. But we did look at an example at the end of how you can just use the Feynman rules and just go straight to the amplitudes rather than going through this whole long procedure above. Okay, so that's the end. Thank you for those who made it to the end. I hope you learned something from the course. And I hope I've had some chance to interact with you as well, rather than just talking to this video screen. And yeah, if you have questions or anything still unclear, you can email me. I'm happy to talk further about the subject. Okay, so thanks very much for watching.